Okay, so there's a few things that we are talking about in today's notes. In today's notes, we're looking at graphing. The first thing we're doing is what's called end behavior, or the far left and far right behavior. You saw that in Algebra 2, I believe. We're finding zeros, which we've done before. And then the last thing we're doing is we're going to look at a graph, and we're going to identify some pieces of information. Okay, so first thing, end behavior. Looking at the definition at the top. End behavior tells us what happens to the far left and far right of a graph. It is based on the leading term. So if you could write this down, when I say leading term, I mean the term that has the highest power. I do not mean the first term. So sometimes in the equation, the first term is the one that has the highest power, but it's not always. All we care about is the term that has the highest power. What we are looking at to determine the end behavior is the degree and the lead coefficient. For the degree, the power, what we care about is that power even or is that power odd? If the power is even, our graph will start and end the same. If our power is odd, our graph will start and end differently. So an example of an even degree would be up and up, or down and down. That's the end behavior. To the far left, the graph goes up. To the far right, the graph goes up. Something happens in the middle. When we say end behavior, though, we don't care about the middle. All we care about is far left, far right. Odd, on the other hand, will start and end differently. So if we start up, the other side would end down. And again, something happens in the middle. We don't care what happens in the middle. What we care about is that to the far left, the graph goes up, and to the far right, the graph goes down. So that's the first thing that end behavior, that's the first piece of end behavior. The second piece of end behavior is the leading coefficient, so the number in front of the term. What we care about is that lead coefficient positive or negative? And that lead coefficient will tell us how the graph ends. Okay, for example, a positive lead coefficient will end up. So if we have a positive lead coefficient, our graph will end up. If we have a negative lead coefficient, our graph will end down. So example 1 would be a typical example that you would see for end behavior. It says determine the far left and far right behavior of each function. So far left, far right is the same as end behavior. Here's what you're going to do. You are going to determine the leading term, the term with the highest power, and that's this term right here. The other three terms we don't care about. So all we care about is that term. Those three we can ignore. We are looking at the degree. So our degree is 4, which is even. So the 4 doesn't really matter to us. The fact that it's an even power is what matters. Okay, then we notice the number in front of that term, the lead coefficient, is -1, and what we care about is that that's negative. So there are two ways that you can express far left and far right behavior. One is with a picture. So that's what we're going to do. Here's how we would think through that picture. Starting with the lead coefficient. If our lead coefficient is negative, what that means is our graph will end down. So that's what you're going to start with. We know the graph ends down. Because our degree is even, we know that our graph will start and end the same. So if we end down, we also start down. And again, there's something that happens in between, we don't care. We have no care at all as to what happens in between. We just want to know the graph starts down, ends down. You can express your answer like that and be done. The other way that you can express your answer, so write this down so that you know both ways, is in words. You would say far left and far right. And that's just looking at the picture. On the far left of the picture, the graph goes down. On the far right of the picture, the graph also goes down. On your homework, I will accept either answer. So if you express it as a picture, that's great. If you express it in words, that's great too. You need to be able to read both or write in both, but I'm not going to require you to use one format over the other. Questions for me before you try B? Okay, please take 1 minute and try B on your own. Okay, is anybody confident enough to talk me through any part of the picture? John, thank you.
Degree is odd, so this is differently.
Okay.
Leading coefficient is not even positive.
Okay, so our lead coefficient is a positive 1.
Yes, so far right will be up and far left will be down.
Okay, very good. So what we should have done, leading coefficient is 1. What we care about is that number is positive, so we will end up. And then like John said, our degree is odd, so we will start and end differently. If we end up, we started down. If I asked you to put this in words, it would say far left equals what? Down. Far left equals down, far right equals up. Please, I cannot stress enough, don't just look at the first term. Look at the term that has the highest power. Sometimes it's at the beginning of the equation, sometimes it's the middle or the end.
So the top of the graph, that tells us that we write it like, when you put an arrow whether it's like odd or even. And the bottom one tells us whether it's like up or down.
No. What do you mean by top and bottom? This?
Yeah, like the top of the graph and then the bottom of the graph.
No. The lead coefficient
Yeah.
tells us the right side of the graph, if it's going
Oh,
up or
okay.
down. The power will then tell us what the other side, the right side of the graph
Okay.
is. Okay, that is the first thing we need to talk about today. Questions about that before we move on? Let's move on then. Okay, if we are finding real zeros of a function, when I say 0, what does that mean? X-intercept, it means the output is equal to 0. The output is equal to 0. Most of the time, that means y. So when we say 0, we mean the output is 0. Y is 0, not x. Two things for you to remember. First of all, when we say 0, that's the same as x-intercept. So x-intercept means y is 0. How do we know how many zeros there are? How do we know how many zeros there are when we look at an equation like 2a? Power. Yeah, the power or the degree. So the number of zeros will be equal to the power. Okay, so 2a. Find the real zeros / x-intercepts of each polynomial by factoring. So again, real 0 means that the output is 0 or y is 0. So we get 0 is equal to x to the 5th, so subtract 10x cubed plus 9x. And we're going to factor. First step to factoring here. Anybody? Take an x out. Take out a GCF. When we do, we get x to the 4th, subtract 10x squared, add 9. That will factor again then. We're looking for two numbers that multiply to 9 and add to negative 10. Multiply to 9, add to negative 10. Beautiful. Can you raise your hand next time, please? But yes. Negative 9 and negative 1. So it gives us x squared minus 9, x squared minus 1, because this middle term is x squared. So then we have to ask ourselves, do these factor again?
Yeah.
Yes, they do. Kira, how does x squared minus 9 factor?
X minus 3 and x plus 3.
Very good. Kira, while you're on a roll, what about x squared minus 1?
X minus 1, x plus 1.
Yeah, beautiful. Thank you. Now, we're going to set all 5 of these equal to 0. So we get our zeros to be 0, 3, -3, 1, and -1. So those are the 5 zeros, or x-intercepts, of our equation, if we were to graph it.
Why don't you split the middle term so it's a,
You could split the middle term. The a value is still 1 here.
yeah, sorry,
You definitely could, though. Alexia, how did we know at the beginning we were going to get 5 answers?
with the power.
Power. X to the 5th, we should get 5. They're not necessarily going to be 5 different answers, but you're going to get 5 answers. You all do B. We'll come back together, go over it, and then we'll take a break. So please do B. This is what I got. -4, -2, and 2. 4 terms. This is where you put the line on down the middle and factor both sides. X to the third, you got to make sure you got 3 answers. This is the one where a lot of times you all get the right answers, but our work is not always as well defined as it should be. Look at your work right now, and please make sure you have equal 0 on every line. If you forget it on one line, not a big deal. If you only put it in the first line and then it disappears, though, I am going to take points off. That is the zeros part. Questions for me on end behavior, the far left, far right, or zeros before we take a break? Let's finish these notes. Last thing we're going to talk about is reading information off of a graph. This is new to you. This I'm going to tell you right away you have not seen. There are 2 examples, the example in A to the left, the example in B to the right. We have to find everything, identify everything in those 5 bullet points at the top. I'm going to do A with you, you're going to do B. Okay, so now we can see all of A. Okay, symmetry with respect to the x-axis, y-axis, or origin. That you've done before. If we look at this graph in A, if we fold it across the y-axis, they're not mirror images. If we fold it across the x-axis, they're not mirror images. It's not symmetric with respect to the origin. So what we are going to say for A is that it has no symmetry. Okay. Then you are asked for maxima and minima. Now what I want you to notice is in the 2 bullet points, there are some differences. There are local and there are absolute maxima and minima. Here's what that means. A maxima is a high point on the graph. Any high points that you see. So in our graph, there are 2 high points. There's one right here and there's one right there. In the past, when I've asked us for a maximum or a minimum, what do I care about, X or Y? Y. Okay, so if we say local maxima, it's going to be this point and this point. But again, it's only the Y value. So the Y value from the first one is 0.4 and the second one is 4.7. So there are 2 local max. Local min, you're looking at the lowest points on the graph. There are 2, there's one here and one here. But what I want you to notice, this point is open. This point is not included. That point does not count as a minimum. That point does not count as a minimum. This one does, though. And again, all we care about is the Y value. So that is our answer for B. In C, when it asks us for an absolute max and an absolute minimum, it is the single highest point and the single lowest point. So for absolute max, we said there were 2 maximums that were local or relative. When you are asked for an absolute, you're picking the biggest one. So this would be our absolute maximum because it's the highest one on the graph. So that's 4.7. There was only one minimum, and it's the lowest point on the graph. So we say that that point is negative 10. Okay. Intervals of increase. We're looking for every place where the graph is going up. Where the graph is going up. Here, the graph is going down. It's not increasing. Here, though, the graph is going up, and then it goes down again. So the only place where the graph is increasing is right here. We express increasing and decreasing in terms of x. So we start increasing when x is negative 1, all the way until x is 1.3. So our increase is from negative 1 to 1.3. And it will always be open brackets or open parentheses. Okay, lastly, for decrease. There are two places we are decreasing on the graph. We are decreasing from here to here, and then again from here to here. Again, though, all we care about is x. So the first one starts at negative 2.2 and goes to negative 1. So we have negative 2.2 to negative 1. And then again, we have 1.3 to 2. So that's from here. X is 1.3 to 2. Because there's two of them, how do we connect them? Charlotte?
Do we, like,
We do, the U. Mine should all be written on the same line, but I ran out of room, so. Okay. Any questions on that? Some of it you've seen before, like the symmetry you have, but the maximum, minima, and the intervals are new. Okay, you right now do B. Answer those same 5 questions for the graph in B, please. My answers are in black. So this does show symmetry with respect to the y-axis. If we were to fold this on the y-axis, it would be symmetric. There are 2 local maxima. So any peak is a maximum. This right here is a maxima at negative 9. That is also a maximum at 6.5. There's 1 local minimum. Well, really there's 2, but they have the same y value. Kenny?
Do you have to put in like a certain order? Is it fine?
No. Yeah, any order is fine. And the graph is increasing in 2 places, decreasing in 2. Make sure you have a U in the middle. Make sure that you have an open circle. I want to address one thing real quick with you. Any questions on those before we talk about one last thing? Okay. Let's say that our graph looked something like this. Okay. My first question, does this have an absolute minimum? Absolute minimum. Does this graph in green have an absolute minimum?
yes.
Yes. Okay. Absolute minimum would be here. Does this graph have an absolute maximum?
No.
The highest point on the graph, is it included on the graph? No. So there's a highest point, it's not included though. There's no absolute maximum. Are there any local maximums? Yes. Right here, right there. So we need to pay attention to the open closed circle.
Would the highest point be included in the local maximum?
No.
Or is
Good.
it would be included in even?
Nope. It would be included in an interval of increase or decrease, but not maximum or minimum.